Hi, this is Johannes Kind, and I would like to welcome you to the fourth issue of the FastScan market campaign. Today's topic is fast PeakForce imaging of purple membrane. All of the data obtained on the FastScan is great, but pay special attention to this presentation, because what the FastScan has done here on this ultra-challenging and well-known sample of Bacteriorhodopsin is truly amazing. I say this because the videos we will show today illustrate record-setting resolution and speed. Likewise, the productivity and ease of operation of the system allow fascinating dynamics to be easily observed. All these things are 100% unique to FastScan and Bruker, and in this presentation you will see how PeakForce tapping and FastScan enable all this using the Bruker first and onlys of ultra-low amplitude PeakForce tapping, which enable resolution typical for ContactMode and well beyond TappingMode with no lateral force. Direct force control to eliminate thermal force drift, and of course FastScan speed to enable the study of sample dynamics. This is a truly remarkable set of data and tour de force, so let's get started. When you present this to customers, the PowerPoint presentation will start with an introduction and background of the measurement. We will cover this later. So what you are seeing are two purple membrane patches. At the resolution we are imaging, you do not expect to see the lattice that we saw on the previous slide. Instead, we are looking at the self-assembled patches on a mica surface. Bacteriorhodopsin self-assembles into purple membrane patches on a mica surface under the right buffer conditions. The movie shows the dynamic edge of two adjacent patches, integration of small patches, and the addition of further Bacteriorhodopsin during continuous imaging. So next I want to point out when these things happen in the movie to you. So we have a patch on the left and on the right, and on top of the right patch there is another patch, and it seems to sort of flow like a waterfall into the gap between the two big patches. And well, we'll see it on the next loop again. So there is a little piece of the overlapping patch on the right hanging into this gap, and over the first few frames, right in the circle now, it's separating from the right patch, the right overlaying patch, leaving this sort of extension there in the gap. And now this patch is being integrated into the left large patch. So let's see this again. Here it's still attached, and here it's already integrated into the left patch. The same thing is happening at the top edge the second time a circle appears. So this time there is a separate patch, and now it's being integrated. The other thing we are seeing is that the edge of those two patches is not static; it's always in motion. So it's almost like the surface of water. It's always moving around a little bit. And what's really important here is that this is not happening just in one direction. So it doesn't seem to be strongly AFM scan driven or anything. The gap is widening and it's getting narrower again. Now it's wider again. Also on the top edge you see quite a bit of motion, and so this is happening everywhere. This seems to be what the patch natively wants to do on the surface, maybe with some motion in the water, but definitely not tip driven. And then the next thing we did to make it a little more interesting is after a certain number of frames we injected a little bit more of the purple membrane solution right now. And right now you're starting to see extra proteins appearing, and they're sort of sitting on top of the patch. And well, let's start this over. Here comes the extra protein, and what's interesting is that they seem to collect on top of the other patches, but they don't necessarily self-integrate. So it might be that the self-integration mechanism needs to be from the same plane rather than from on top of the other patches. But This is something we cannot conclusively say from this one short movie, but it's definitely something that a researcher is able to investigate using this time resolution capability offered by the combination of fast scanning and the robustness of PeakForce tapping. So a lot of these particles collect on the surface, and they also seem to be driven close to the edges. Let's watch this one more time. And we see that these little particles are very mobile on the surface, and they tend to move towards the edge, but then they are sitting there. And these are definitely all things that can be studied in a little movie like this. Of course, we are doing PeakForce tapping in fluid here. The PeakForce tapping frequency is the maximum frequency allowed in the FastScan system, which is 8 kHz, allowing 8,000 pixels per second, which then works out as a line rate of 11.2 lines per second and a tip velocity of 24 microns per second at a resolution of 256 squared. And the whole movie consists of 75 frames. Another nice thing to point out is the little white area on top of that second patch on the right-hand side. Because we don't know exactly what it is, but it is a feature, and it seems to be very static in the image. In fact, it doesn't really move around at all throughout the process of taking this little movie, which really shows the good stability provided by the FastScan system to take these movies. Lateral stability becomes much more important when taking movies, because over a single frame, while it can cause a little distortion over a whole movie, it will really shift around the field of view and become much more apparent and much more annoying. So the stability seen in this little movie here is a very good thing for studying dynamics. In the caption under the image it says purple membrane patches on a mica surface self-assemble under the right buffer conditions. Now, in case you have customers who ask what those right buffer conditions might be, I put a little note into the slide notes for you. Now we are coming to an especially challenging and therefore especially exciting piece of data. What you see on the left side is the FastScan system in a real-time view imaging purple membrane on the lattice scale. This data was obtained with Broadband C probes and in PeakForce TappingMode and fluid at a modulation frequency of 8 kHz. And here's the key, with a PeakForce tapping amplitude of only 2 nanometers. Traditionally, this type of resolution is only reached in ContactMode imaging. ContactMode works on these samples because there is almost no topography. The topography on top of the proteins is on the order of half a nanometer, so there is very limited lateral forces. However, what makes ContactMode imaging here especially challenging is that very excellent force control is required. Basically, forces above 400 piconewtons will destroy the sample. In ContactMode, the force is represented by the deflection of the cantilever, with the assumption that the zero deflection adjusted once in the beginning is going to hold up. However, a soft cantilever is also a bimetallic strip, so this zero force will drift and therefore the imaging force will drift. And so it is very hard to maintain a stable imaging condition over one or even several images in contact mode. In tapping mode, typically this type of resolution cannot be achieved, with the advantage from the PeakForce tapping mode that zero force is reset on each individual pixel. A force curve is taken on each pixel and the beginning of the force curve represents zero force. Therefore, force drift, thermal force drift is not really an issue. What is interesting and exciting here is that it is possible to achieve this type of resolution at all with a mode that is not contact mode, basically with a cantilever modulation based mode. There's also a big academic discussion going on about ultra-low amplitude tapping. Ultra-low typically meaning on the order of 1 nanometer. Well, this was 2 nanometers. There's a little bit of background topography visible across the image, and the purple membrane self-assembles on top of a mica surface. and there can be slightly varying attachment conditions between the mica and the purple membrane, which then leads to a little bit of topography. And this shows that in many places the purple membrane proteins are actually more bound to their neighbors than they are bound to the substrate, which again illustrates how fragile the sample is. This wonderful data was taken by Shuiqing Hu of Bruker in collaboration with Isa Medalsi from the Daniel Müller lab in Basel. After background subtraction, we can now see in most areas the trimeric structure of the Bacteriorhodopsin protein complexes. In the magnified area, we can see that there is quite a bit of detail on there, and actually with a 512 by 512 pixel resolution, what we are seeing is probably at the moment limited by the number of pixels used in the image, and is not necessarily the resolution limit of the technique. Comparing the structure from the protein data bank with our image, we can recognize the three domains that are rotated by 120 degrees. We can also see that on many of the protein complexes the center pore is well resolved. This makes a lot of sense in PeakForce tapping, since one of the strengths of PeakForce tapping is the tracking and imaging into tight, narrow gaps and channels without dampening. At the top insert, we see the 2D FFT analysis of the image. We see several orders in here. The first order is the unit cell of the 2D crystal. The higher order represents the repetitive substructure of the individual protein complexes. When we compare the quality to the image on the introductory slide, that we'll talk in a little more detail later, we see that in the image that was published in the 2008 review by Andreas Engel, there is even more detail to be seen in that image. Of course, he is a leading pioneer in this field, and he has over a decade of data to choose from when publishing image of this structure in a review. When you compare this to our effort, probably the time and effort that went into that high quality image in total is probably on the order of 1,000 higher, so it can be assumed that that is the absolute limit of achievable resolution with current techniques. While in our image we actually can't assume that. This was a pretty quick effort and probably represents by no means the limitations of the technique. The resolution is clearly beyond that achievable by TappingMode, and may be comparable to most efforts done in ContactMode on these samples. And history will then show, ultimately, if PeakForce tapping actually has any disadvantage with regard to resolution compared to ContactMode on these samples. At the same time, of course, it has the much higher ease of use and robustness. So we are summarizing all of this in the conclusions. First, the scientific result, since this is the format that we are going with for these little seminars. So the scientific result here, high-speed PeakForce tapping was used to image Bacteriorhodopsin. To study patch dynamics with 22 seconds time resolution. So every 22 seconds you get a new image. So if you resolve a process with that, you have 22 seconds time resolution. And on the other hand, on the lattice level with 58 seconds per frame, with good resolution of the 3 Bacteriorhodopsin domains, using a PeakForce tapping amplitude of only 2 nanometers. Now, how does this relate to Bruker products? The data was obtained by the combined capability of low amplitude 2 nanometer PeakForce tapping in fluid, and the increased imaging bandwidth enabled by the Dimension FastScan AFM, and small broadband cantilevers. PeakForce tapping achieved resolution typical for ContactMode, and probably beyond that of TappingMode. PeakForce tapping simplified force control due to its immunity to the thermal force drift. And the FastScan speed enabled the study of sample dynamics. Let's take a quick look at the background of this interesting and also very challenging field of AFM research. Purple membrane is a two-dimensional protein crystal formed by the membrane protein Bacteriorhodopsin, or BR. On the right-hand side you can see the protein structure of Bacteriorhodopsin in its native conformation. The source of this data is the Protein Data Bank and has been explored by X-ray crystallography. The complete structure and function of Bacteriorhodopsin had only been discovered in the year 2000. BR consists of 3 identical protein chains, arranged by a 120-degree rotation. Bacteriorhodopsin is found in archaea, the most notable being halobacteria. In these organisms, Bacteriorhodopsin acts as a light-driven transmembrane protein pump, converting light into chemical energy for the organism. High-resolution imaging of membrane protein crystals, like purple membrane, is broadly recognized as one of the most taxing samples for the performance of an AFM, with regard to resolution and force control in fluid. A pioneering group in AFM imaging of purple membrane was the group of Andreas Engel at the Biozentrum in Basel. Both collaborating group leaders in this application piece, namely Daniel Müller in Basel and Simon Scheuring at Institut Curie in Paris, each a leading AFM membrane protein expert in his own right, came from the Andreas Engel lab. The AFM image on the right, from a 2008 review by Andreas Engel and Hermann Gaub, represents the pinnacle of a decade of membrane protein research by AFM with regard to its quality and resolution. So this is a pretty good baseline when judging further data taken on the sample. A little more background on the 2 collaborators. Simon Scheuring is an avid Bruker reference. He is a member of the high-speed AFM consortium that we are also a member of, together with a couple of other researchers in Europe, and also with Toshio Ando, one of the pioneers of high-speed AFM imaging in Kanazawa, Japan. Daniel Müller uses both Bruker and JPK equipment in his lab, the Bruker equipment mainly for high-resolution work and as of recently on a multimode 8 for PeakForce tapping. Both are very impressed with the FastScan system. Let's enjoy the picture one more time, because I really like it. I hope you are as excited as I am about this new piece of data that's really showing very high performance, very high resolution imaging on a very fragile sample with good stability enabled by PeakForce tapping and very good time resolution achieved with the FastScan system. I hope you are as excited as I am, and in case you're not sure whether you are excited, just go to your nearest expert high-resolution protein imaging customer and show the data to them, and then watch their reaction, and then you will be equally excited about this data. Have a good day, and stay tuned for the next piece in this series.